Hello, and welcome to Aggressive Physics. Today is day 65, and what we're going to discuss today is work. Now, work is a term that we use in our everyday language, and it can mean a various amount of things. It could be the job that you go to, the work that you do for school. It can refer to yard work or things like that. The problem is in physics, work has a very specific definition, and it actually involves forces being applied and objects moving. And the key to work is that the force needs to be applied in the direction of motion. So only the force that contributes to the motion and the direction it's moving will actually do work. So in many cases, if you're pushing things at angles, a lot of that force is going to be wasted. Now, of course, ergonomically, you need to have handles on things like lawnmowers. We can't push a lawnmower while crawling on the ground. It's not very viable. So you have a force that you have to push down, but the more you apply that force in the forward direction, the better usefulness of that force will be to do work on the lawnmower. So what we're going to be able to do is calculate the amount of physics work done, but only if we use the force in the direction of motion, and only if there's motion involved at all. You can push on an object and it doesn't move all day long, and you will be doing no physics work. You may be getting tired, you may be fatigued, but you're not actually doing any physics work. Now, in terms of the equation for work, it's simply work is force times distance. Now remember, that force has to be in the direction of motion. So if there's angles involved, you may have to break legs or resolve the vector into components first. And only the vector pointing in the direction of motion will actually matter. We can simplify the equation even further, since F equals ma, to work equals mad. And that's easier to remember the equation because remember, work makes you mad. You don't want to do work typically because you have inertia and you want to have the tendency to do what you're currently doing, which is usually nothing. But in this case, if you remember MAD, you can calculate the work as well. Now we do have to discuss the unit. Force is newtons and distance is going to be measured in meters. Now since force and distance are both, well, force is a vector and distance is not, work is going to be a vector quantity. We're going to have to worry about the direction that work is being done. Now, with that being said, what we do is we use the variable Joule to represent work. So newtons times meters is also known as the Joule, and we use capital J for that, and that's our simplification of the unit. Now, the biggest problem with that is that we just talked about impulse, and impulse was also a capital J. So beware of what is talking about impulse, which is J, and what is talking about work, measured in joules. So that's an issue you need to work out. Now, why are we using the Joule at all? Well, James Prescott Joule did a lot of work with energy transformation and work going into different forms. So what he did was he actually figured out a relationship between heat, energy, and electricity dealing with work. One of his famous experiments is one in which he took paddles and placed them in a glass or beaker of water. And he had masses hanging with pulleys to the paddle, and the paddle would spin. And as the paddle spun, it would give energy to the water, so the water would heat up. And what he was able to do was find a relationship between work and energy. You'll find later that we use the same unit for energy, and in many cases work and energy are interchangeable. As long as friction isn't present, the amount of work you do will be the amount of energy that's gained by an object. So James Prescott Joule did a lot of work in this field, so we honor him by using his name as the unit for work and energy. Now, there are a number of situations where no work will be done. If you push against a wall and it doesn't move, you're doing no work. If you're holding something up and you're not actually moving it, you're doing no work. Hold your arms out in front of you holding a textbook or a small mass or a cat and hold it for 5 minutes. It's hard to tell me that you're doing no work. And in fact, you're working your muscles, you're doing work in a non-physics sense, but specifically for physics, the term work involves distance. It has to move. So if you hold something stationary, you're not actually doing work. If you hang from the chin-up bar for an hour, you are doing no work. You're just hanging. If you were to chin yourself up or pull yourself up, then you are doing work. Only when you're moving in the upward direction. On the downward motion, gravity's doing the work for you. Now, in addition to that, if you are holding a tray and you're actually walking sideways, and I'm thinking right now carrying a tray of glasses or food in a restaurant or something like that, the person who is carrying the tray is doing no work on the tray. Think about the direction they're applying a force. It's upward. What direction are they moving? Sideways. Well, upward and sideways are perpendicular. There's no work being done. Now, I understand that waiters and waitresses are actually doing work. They go to work. They deserve gratuity at the end of a meal. But in terms of physics work, what's actually doing all the work is friction. If there's no friction between the tray and the plates or the tray and the glasses that are being carried, they'll slide right off the tray and onto the ground. So if you want to thank anyone for getting your drinks to your table or your food to your table in a restaurant, it's really friction that's doing all the work. Now, that being said, anytime you have a perpendicular force to the motion, it never does any work. So a prime example for assessments, a prime example that is often asked on assessments, is whether or not centripetal forces do work. And in fact, centripetal forces do no work. If you think about it, the force is inward when you deal with a centripetal force, and the motion is tangent to the circle. Well, tangent and inward are perpendicular. They're 90 degrees apart. So if you're ever asked a question about a centripetal force doing work, the answer is going to be 0. So just be aware of that when assessments come along and you're asked these tricky physics questions about work. You need to have a force in the direction of motion. For centripetal forces, such as the gravity holding the moon in orbit, or the friction holding a car in a tight circle when it makes a turn, or possibly a person spinning around perhaps a yo-yo around their head, or a bucket of water or something like that. The arm in that case, or the tension, the friction, the gravitational pull, all do no work. In fact, a famous statue in New York City near Rockefeller Plaza is of Atlas holding up the Earth. Well, Atlas holding up the Earth is actually doing no physics work. I don't know why he's so tired all the time. He does no physics work. Now, what we can do is some practice problems dealing with work, and we can calculate work if the force is all in the right direction, in the same direction as motion, or perhaps maybe it's at an angle, and we can only use part of the force to calculate the amount of work done. All right, let's talk about work. Work in physics is simply force times distance. So our equation is W equals Fd, which we could simplify if we needed to as MAD. The key is that the force must be in the direction of motion. So if the distance is horizontal, only the horizontal force will do work. If the motion's vertical, only the vertical force will do work. If we happen to have a situation where we have an angle involved and we have to resolve the vector into components, either x or y, the work will be the component that is in the direction of motion. So in this case, if we had a horizontal displacement, then the x component would do work, which would end up being F cosine theta, and then multiply that times d. In this case, what I showed before, it would just be strictly Fd because all of the force is in the direction of motion. Now, you could even think about it like this. It's always F cosine theta, but in this case, theta is 0. So if theta is 0, then cosine of 0 is 1. So we could look at it like that. I just think it's easier to remember that if it's sideways, we use all the force. If it's at an angle, we only use the force pointing in that direction. That being said, let's assume that this force is 250 newtons and it travels 3 meters. And we'll do the same thing here. 250 newtons, travels 3 meters, but the angle now is 40 degrees. Okay? Now on the left side, W equals FD, 250 newtons, 3 meters. So that's going to be 750 Newton meters, which we call the Joule, capital J. For the other one, W equals F cos theta D. And you could break legs first and then just plug the number in here. But what I'm going to do is just continue on with my 250 times cos 40, and then multiply that by 3. And in this case, you have 574.5 Newton meters, or 575, we'll just round it, joules. Now, we did the same amount of force, but because it was at an angle, not all of that force did work for the second example. So if it's all pointing in the same direction as the motion, it's more efficient, if you will. It gives you more total work done. If some of it is at an angle, you're wasting some of that force, and it's going to be less total work done. Now, since motion has to occur for work to be done, W equals FD, there are two ways in which a force can do no work. And if we have no motion, you're not going to do any work. If you try to push against a wall, and here's the wall, and you push, and it doesn't move, then no work. If you were to hold something, like weights or something like that, and you have freakishly long arms apparently, and you just stand there and you hold them out for 30 seconds. During the time that you're holding them stationary, you're doing no work. Now, one very specific case of no work being done is centripetal forces. So, classic questions asked on Regents assessments, introductory physics courses throughout time have always asked about the following. If we're spinning we'll call it a ball on a string, and we have the tension going inward, okay, tension's going inward, how much work does tension do? And the answer to the question is strictly 0. Z-E-R-O. Now, here's why. The tension's inward, and the direction, as we know from before, is tangent. Well, how many degrees apart are tension and tangent in this case? 90 degrees. They are perpendicular vectors. So, in this case, tension in the rope is going to do no work. If we have the Earth and we have the moon orbiting the Earth, what is the force keeping it in the circle? Well, it's the force of gravity. In this case, no work, because it's perpendicular to the direction of motion. So in order for work to be done, it has to move, and some of the force has to be in the direction it moves. Centripetal forces do no work. So anytime that's asked, it's a trick question. They want you to spend about 20 minutes calculating things, and the answer becomes 0. So watch out. Now, students often complain about the amount of work that they have to do for school. And one of the things that a lot of students complain about is typing out 500-word essays. And I just picked 500 because that's a standard size essay. I want to come to a conclusion about the actual amount of physics work that's done. So what I did is I took a keyboard and I placed a mass on the key so that it would press down, because the keyboard requires a certain amount of mass to activate, and there's a little spring on it. and it will push down and then connect a metallic connection so that the signal sent to the computer to then show the letter on the screen. Well, I found that the mass required was about 65 grams. And I'm saying about because it was close to 65. Some of them required a little less. Some of them required a little more. I ended up with 65 grams as a good average. Now, I also measured the distance the keys had to move. And I'm pretty sure the key motion was standardized. It was about 0.5 centimeters. So it required 65 grams, and it moved 0.5 centimeters. So how much work is done in a key press? Now, of course, you can apply a larger force. Some people are very heavy with the keyboard, so they push down hard on the keys. Some keyboards require more force. But in this case, with my keyboard that I used, the force would be the same as gravity pulling down, so 0.065 kilograms times 9.8 meters per second squared, and the distance is 0.005 meters. So how much work is each key press? Well, if we multiply these three numbers, 0.065 times 9.8 times 0.005, I get 0.0032 joules. Now that's per key press. So let's think about how much the total amount of key presses will be. Well, we have a 500-word essay. And I'm assuming that there'll be some thes and ands and uhs. But if you're trying to impress your teacher, you're going to use words that are hopefully longer than 3 letters. You'll use some 6, 7, 8-letter words, hopefully. That will all average out to approximately, I just think, maybe 5 letters per word. Now that means you have to apply 5 times 500, which is 2,500 key presses. So far. We're not done yet. Now, inevitably, in between each word you need a space, so you have to hit the space bar. And the space bar, I'm going to assume, has the same force required, minimum force. So it will take 0.0032 joules of work to press the space bar. Now, you'll also probably make some mistakes, so maybe use the backspace. At the end of each sentence, you'll need to use punctuation, maybe a period, maybe a question mark, things such as that. Maybe in some cases you're doing inline parenthetical citations. So you may have to use parentheses. That being said, let's just assume that each word itself requires 3 presses for punctuation, spacing, and backspace. Give or take. Now that's 3 times 500, or 1,500 presses. 2,500 and 1,500. 0, 0, 0, 2, 3, 4,000 presses. Well, 4,000 presses times 0.0032 joules. Let's see what we get. Approximately 12.74 joules. Now, let's just think about the fact that 12.74 joules can be converted to potential energy. Now, your calculator, let's just say it's about half a kilogram. How high would you have to lift your calculator in order to have the same amount of energy? Well, in this case, we have the work that you would need to do is overcome gravity, and you'd have to lift it a certain height. This 12.74 joules is your work. The force, you'd have to overcome 0.5 times 9.8. And if we did 0.5 times 9.8, you get 4.9 newtons. So the force is 4.9 newtons times D. So 12.74 divided by 4.9 gets me the distance of 2.6 meters. And I'll write that over here. 2.6 meters is the distance. We'd have to lift the calculator. So you take your calculator, lift it over your head once. That's about 1 meter. That's about 2 meters. Lift it maybe back to your pocket up from the ground again, and there's your 2.6 meters. So lifting your calculator 1.5 times would be equivalent to doing the same amount of work for a 500-word essay. Now that's physics work. It doesn't involve the mental preparation and other aspects. It is strictly force times distance. To revisit the 500-word essay problem, the one number that I was a little concerned with was the mass of the calculator. And actually I found the mass of the calculator to be about 250 grams, not 500 grams, which makes it 0.25 kilograms. Now, if you're trying to lift that 0.25 kilogram mass, what's going to happen is you're going to have to overcome gravity. So you're going to have to overcome the mass times the acceleration of gravity, and you could figure out the distance required to do that. W is 12.74, and since we were twice as big as it should have been, what's going to end up happening is if you take 12.74 and divide it by 0.25 times 9.8, you'll end up getting 5.2 meters, which is a significant amount of distance. You take your calculator and lift it up above your head. Do that once. Put it back on the ground. Do it again. That's about 4. Lower it. And then raise it to about your chest or your abdomen. And that should be just about 5.2 meters. Now, of course, different people have different heights. So 5.2 in terms of 2.5 lifts is relative. Now, if we had a person who was, let's say, 110 pounds, which is 50 kilograms, 12.74 joules equals 50 kilograms. Now you're overcoming 50 times 9.8, and you want to find the distance required. Well, in that case, 12.74 divided by 50 times 9.8 is going to get us a distance of 0.026 meters, which is 2.6 centimeters. So that might be able to put it into a little more perspective how little work that actually is in terms of physics work. That's taking a 110-pound person and lifting them a total distance of 2.6 centimeters, which is just about 1 inch off the ground. Or if they're doing maybe a chin-up, they just have to lift themselves 1 inch from their rest position. So the amount of total work is a specific number, 12.74 for the essay, but in terms of physical activities, it will be lifting a calculator 5.2 meters or lifting a 110-pound person about 1 inch. Now let's look at another problem with work, and in this case what we're going to do is shovel the driveway. Now, of course, depending upon the type of snow and the size of the driveway and the type of shovel you have, that will determine how much actual work you're going to do. But for this example, let's say it's a light and powdery snow, and all you're going to do is push down on the handle, and that's going to push the snow in strips across the driveway. We're going to do the problem assuming that we have a 10-foot wide driveway. That's about 2 car lengths, give or take. And then the length, we're just going to say it's approximately, if you could fit 2 cars on it, we'll say it's 25 feet. Now, to make our lives easier, what we'll do is we'll say that this is approximately, for the shovel, 1 foot. So when you are shoveling, you're actually shoveling 10 strips of 25. So the total distance you're going to move would be 25 feet, because you have to go 10 times, well, I guess you could go forward and backwards. It's a flat driveway. 25 times 10, which is a total distance of 250 feet. Now, that being said, we need to convert to meters. So that would be 3.28 feet. Let me get rid of that. Let me make that look a little prettier. 3.28 feet is 1 meter. And if I do 250 divided by 3.28, I get 76.22 meters. So that's the total distance. Now, what about the force? Now, the force is going to be applied along the handle, and that is going to produce an angle of some sort with the ground and with the handle itself. Now, like I said, we may be applying a force of a varying value depending upon the snow, but let's just assume it's 75 newtons. And this is just a standard shovel where it's a 45-degree angle. Now that means you'd have to break the legs, 75 times the cosine of 45, which is 53.033 newtons. And then, of course, because it's a 45-degree triangle, you're going to have the same force in both legs. Now, only the x direction matters. So that's the one that's going to actually supply work. Now, work, as we know, is force times distance. The force is 53. We'll just round it to 53. The distance was 76.22 meters. So 53 times 76.22 gets me a total amount of work of 4,042 joules. Now, if you remember, the value of the essay was around 13. 13 joules to type an essay, 4,042 joules of physics work to shovel the driveway. If you have a bigger driveway or you have heavier snow, it's going to require even more.